Hello, hi. Am I audible? Someone at least respond in the chat. Am I audible? Okay, so let's begin. This is week 6 of the course Introduction to Statistical Mechanics. And so let's begin with week 6, assignment 6. This week was majorly about ferromagnetism and Ising model and all. The other topics, the specific heat topic that was covered, isn't exactly being covered in the assignment. Actually, this question is incomplete clearly. The question says, consider the Ising type model H is equal to minus H is equal to minus J sum over I equals 1 to n Si into Si plus 1. Consider this Ising model where Sn plus 1 is equal to Si. Sn plus 1 should be equal to S1, not Si. Another mistake here. This is 1. Basically, we are talking about periodic boundary conditions here. Right. Um, so we have this chain where there are spins located at periodic distances. This is I equals to 1, 2, 3, 4, 5, etc. Now what we're seeing is that the last one is actually connected to the first one. So then we actually turn the chain around so that the last one is actually next to the first one. Okay. So that's why Sn plus 1 is equal to S1 actually ensures periodic boundary condition. So that all the spin chains have some spin to interact with, at least two spins to interact with. Otherwise, the last one would have only one spin. The first and the last one would have only one spin to interact. So basically, this ensures that each and every spin has two spins to interact. Every spin has the same environment. There are no edge effects, basically. So whenever you have a proper edge where the spin chain actually ends, so in that case, you see something called an edge effect. There is something special that happens at the ends. So we don't want to see any kind of edge effects, which is why we do this periodic boundary condition. So Sn plus 1 is equal to S1. Now imagine that Si can take values 0 and 1 for each I. So at each of these points, I equal to 1, 2, 3, 4, 5, your spin has only two values. It has either value 0 or value 1. There are two values that the spin can take. Okay, so they haven't mentioned anything after that, but the idea is to calculate the transfer function. Okay, so you have to calculate the transfer function, uh, transfer matrix. Basically, you have to calculate the transfer matrix for this particular model, this particularizing model. Okay, so let's go ahead. Firstly, we will calculate the partition function. Z is equal to trace of e raised to power minus beta h. That's our partition function. Here, trace basically means summing over all possibilities, all possible values. So equals trace of e raised to power minus beta. This Hamilton already has a minus sign outside, and here also there is a minus sign. So this minus minus becomes plus. E is for plus beta j sum over equals to 1 to n si. Basically, it has terms of this form: e raised to power beta j s1 s2 multiplied by e raised to power beta j s2 s3 multiplied by e raised to power beta j s3 s4 and so on and so forth. The last term would be e raised to power beta j s n s1. This would be the last term. It would keep on going till that. Okay, and now what does trace do? Trace would basically mean you have to sum over all possibilities of si plus 1, whatever si is, basically all possibilities of si. So here si's can take values 0 and 1. So si 0 comma 1, sum over all of that, e raised to power beta j s1 s2 e raised to power beta j sn s1. Okay, now let's do this. um, let's just take one particular term and consider one particular summation there. Okay, e raised to power beta j s1 s2 e raised to power beta j s2 s3. Okay, we're just taking this one term. I'm just isolating this one term and I'm considering the summation only over s2. Of course, all the other terms still remain, all the other summations still remain. Si 0 comma 1, I not equal to 2 because 2 I have already considered here, and all the other terms are also here. It is for beta j sn s1. Everything else is here, just that I am isolating this particular term. Okay, now let's do this. Let's introduce a terminology. Okay, I'm introducing something called a transfer matrix, which is of the form e raised to power beta j sm sn. Okay, um, basically transfer matrix is a definition only, but why is it exactly useful and what does it do? That also we will see in this calculation itself. But basically, I'll define the transfer matrix in this manner. Okay. So what will be the values of the individual matrix elements? Firstly, there will be four elements. The transfer matrix will be 2 cross 2 because m and n both can take 2 values 0 1 0 1, right? Sm sn. Okay, let's do this. S1 is equal to M is equal to 1, 2, and S can take just actually the notation will become confusing, which is why I'm thinking of what to do here. Here actually the i's that we are writing S1, S2, S2, S3, all these i's indicate the position of the particular spin. But here when I'm writing M and N, I don't mean to indicate the position. I just mean to indicate different values of S that it can take. I just mean there is some S at some SM, some spin, and SN is another spin. Basically, there are two spins, and both can take values 0 and 1. So SM and SN individually can take values 0, 1, 0, 1. But if I write M as 0 or 1 or something like that, then you might get confused with the position of the spins. So that's why I'm thinking what to do with respect to the notation. Um, okay, I'll just actually, yeah, it's better. Let's do this way. So I'll write M as up and down, where up corresponds to 1 and down corresponds to 0, not minus 1. Because here in this problem, we require up and 1 and 0, not 1 and minus 1. So M and N, I will indicate as up and down only. Okay, yeah. So T up is equal to e raised to power beta j s up, which is what? S up, both are 1, which means this is e raised to power beta j. T up down is equal to T down up is equal to e raised to power beta j. 1 would be 0, 1 would be 1. So this is just 1. And T down is also e raised to power beta j 0, 0, which is also 1. So the transfer matrix will have elements in this manner: down, up, down, up. Okay, so down will be 1, uh, down and up is 1, up and down is also 1, and up is e raised to power beta j. So this is my transfer matrix T m comma n. I hope there are no questions here. Here up and down, it literally don't mean as upspin and downspin, as I clearly said, because I want to avoid confusion with the S1 S2 notation that we already used, which is corresponding to the lattice positions. So that is why I'm using just S up and S down as the notation. So TMN, basically TMN is a transfer matrix, um, and it will contain all the possible values of the term e raised to power beta j SN. As we vary m and n, it will cover all the possible values. So it will basically form a matrix, and that's why it's called a transfer matrix. This is something called a transfer matrix, and its individual elements talk about the value of the term e raised to power beta j SMSN. Its individual term talk about the value of this particular term. So that's what a transfer matrix is in this case. Okay, I hope there are no doubts here. So basically what transfer matrix does here is that because you define a transfer matrix in this manner, we can actually write Z in a particular fashion. So here, by the way, first question is already answered here. We're moving on to the next question now. Z is equal to, okay, let me actually copy and paste the next one. The eigenvalues of the transfer matrix are, that's the next question. Okay, so the next question is, what are the eigenvalues of the transfer matrix? Right, so again, even eigenvalues can be found out very simply. Okay, since we've already written down the transfer matrix, let's find the eigenvalues first. So T is the transfer matrix. Actually, here there won't be Mn. Should remove Mn. This is the transfer matrix. So T is equal to 1, 1, 1 e raised to power beta j. Eigenvalues of this matrix. How do you get an eigenvalues of the matrix? 1 minus lambda, 1, 1 e raised to power beta j minus lambda, where lambda is the eigenvalue. The determinant of this is equal to 0. Gives me the eigenvalues, right? Okay, so let me define x as e raised to power beta j, as they've already said. X is e raised to power beta j. So therefore, I have determinant of this 1 minus lambda x minus lambda minus 1 is equal to 0. So x minus lambda x plus lambda square minus 1 is equal to 0. Therefore, lambda square is x to 1 minus lambda minus lambda minus 1 is equal to 0. Minus lambda minus 1 is equal to 0. Therefore, lambda is equal to plus minus b, which is lambda minus 1 plus minus square root of b square, which is lambda minus 1 the whole square, plus 4 into lambda plus 1. Oh wait, that's really bad. What am I doing? I got confused between the terms. Sorry. I have to find lambda, and x is a constant, known constant. Sorry, minus lambda into x plus 1. Lambda square minus lambda into x plus 1 plus x minus 1 is equal to 0. Therefore, lambda is equal to, using the quadratic formula, minus b, which is x plus 1 plus minus square root of b square, which is x plus 1 whole square, minus 4 ac. It's 4 into x minus 1 divided by 2. Okay, so this is lambda is equal to x plus 1 plus minus square root of x square plus 2x x square plus 2x minus 2x, because there is a minus 4x outside. I'm basically directly evaluating the entire term. There's plus 1 and there is plus 4. So plus 5 divided by 2. So this is lambda. There are two values of lambda. So x plus 1 plus x square minus 2x plus 5, x plus 1 minus x square minus 2x plus 5. Clearly you can see the answer right here, right? So these are the two eigenvalues of the transfer matrix. Now we've already defined something called a transfer matrix. We have found out the eigenvalues of the transfer matrix. But why is it exactly necessary? We started with an Ising model problem. We wrote its partition function, and then randomly we defined something called a transfer function, and randomly we started doing all of this. So what exactly is this, and how does transfer function help us? How does the eigenvalues of transfer function help us? So that we will see with the next question. So now canonical partition function for the above model is what? And they've also specified a condition for that. So this question will actually answer the questions I posed. The solution of the question will answer that. Okay. So the question is canonical partition function for the above model for this particular case is what? We'll do that, but first so we'll basically calculate the canonical partition function, and we'll written an expression for that. So canonical partition function z is equal to sum over s1 s2 dot up to sn is equal to 0 comma 1. All of these have all the values. This is the meaning of trace. This summation is what trace means actually. This summation e raised to power beta j s1 s2 e raised to power beta j s2 s3 and so on till e raised to power beta j sn s1, right? Now look at this is basically, these are elements of the transfer function, right? S1 s2 till sn is equal to 0 comma 1. Transfer function t1 2. Basically your t1 and 2 indicate the lattice positions and whatever value of spin is there at that lattice position. T2 3, T3 4 dot up till Tn 1. I'm making a bracket here. Yeah, this is it. Sum over S2 T1 2 T2 3. Okay, and the other summations are already there. S1, S3, S4, and so on until Sn is equal to 0 comma 1. Here S2 is 0 comma 1. And here there are other terms T3 4, T4 5 dot up till Tn1. Everything is there. But I am isolating just one term like this. What does this indicate? So T12 is a matrix element consisting of the spins at site 1 and site 2. T23 is a particular matrix element. Basically, it's an element of the matrix which contains spins of the site 2 and 3. And now what I'm doing is the middle index is being summed over. Basically, these two are matrix elements and the middle index is being summed over. When did this happen? Suppose I have two matrices M and N. Okay, matrix M multiplied by matrix n. How do you write it in the terms of how do you write it as the sum over terms? We basically write it as summation m mn ab is equal to sum over c mac n cb, right? So normally whenever you write the multiplication of two matrices and you're writing a particular term of that multiplication, so this is how you write it, and you can see that this exactly is of that form, t12 into t23, and the middle spin is being summed over. So the result of this summation would be, basically what I mean is s2 t12 t23, this summation would give me t13. No, it would give me t square 13. Sorry, my bad. Because t's are all the same. All of the t's are the same. So it will just give me t square 13. And then I do t square 34. T square 13 into t34. So now t square is some matrix m and t34 is another matrix n, and we'll use up the summation s3 now to do this. So the next term becomes t cube 14, and so on and so forth. We'll keep on doing this till eventually what happens is we're left with t raised to power n, and because the final one is 1 only, I'll actually be more elaborate about this. T cube 14. So t raised to power n minus 1, 1 n to t raised to t and 1. This is the last term, and only sum over Sn. Here there is sum over Sn clearly, and sum over S1 is still remaining. Okay, so what is left is S1 t raised to power n 1 1. So this is, what does this mean? This is simply trace of t raised to power n, because this is 1 1 term and we're summing over S1. So basically it's sum over both the diagonal terms. That's why it's trace over of t raised to power n. That's what you are left with finally. So this is my partition function. My partition function basically results to be the trace of the transfer matrix raised to n. Transfer matrix raised to n. This matrix's trace gives me the partition function. I hope this part is clear. I hope this concept is clear. This is why the transfer matrix is very important, because simply raising it to some power and taking a trace of it gives me the gives me the partition function. So that's why transfer matrix is a very powerful tool. Okay, assuming that there are no doubts here, trace of t raised to power n is what I get. Now, to get the trace of this, how do you find the trace of this? See, trace of t raised to power n is also equal to trace of u dagger t raised to power n. U dagger u. Actually, it works either way. That's fine. U dagger u t raised to power n. Because I am saying that u is some orthogonal matrix. So u dagger u is basically identity. So I can insert any u dagger u here. And because trace is cyclic, basically trace A, B, C is also equal to trace B, C, A. C, A, B. Yes. Trace A, B, C is also equal to trace B, C, A. So what exactly we do here is, that's why this trace also is equal to trace of u t raised to power n u dagger. Now, till now, this U was any orthogonal matrix. Now, what we'll do is, I'll talk about a very specific orthogonal matrix which will diagonalize T, the transfer matrix. Now, U is basically orthogonal matrix which diagonalizes T. Okay, so trace of U T U dagger U T U dagger dot 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 till the end I have U T U dagger. Basically, I am opening up all the t raised to power n and inserting u dagger u in between everywhere. There are t raised to power n, there are many terms, t multiplied by t multiplied by t. Between the two t's, I am inserting u dagger and u. Between every two t, I am inserting u dagger and u, which is identity, so I can insert it in between, right? So that's how I open up the entire multiplication, and I claim that this u t u dagger is just some t diagonal, and all these multiplied just give t diagonal raised to n, and I have to find the trace of this. This is basically my partition function Z. Now I know that um, the diagonal form of any matrix is simply just its two eigenvalues in the diagonal and the other terms to be zero. It's the diagonal form of any matrix has its eigenvalues in the diagonal and the other numbers, other terms are zero, right? So that's why, because partition function is simply its diagonal form raised to n, and its diagonal form just has eigenvalues in the diagonal. So Td raised to n is just lambda 1 raised to n, lambda 2 raised to n, 0, 0. And Z, which is the trace of Td raised to n, is simply lambda 1 raised to n plus lambda 2 raised to n. This is my partition function. So simply, how do I evaluate my partition function in this scenario? In this case, my partition function is just the eigenvalues, first eigenvalue raised to n plus second eigenvalue raised to n. The eigenvalues are of the transfer matrix. This is what gives me a partition function. I hope there are no doubts here. I hope this explanation is clear. This is actually done in the lectures. I'm just revising it for the purpose of completion. Okay, assuming there are no doubts, moving on. Now, what is the question asking us to do? The canonical partition function for the above model for n much greater than 1. The question is for n much greater than 1. And what difference does it make? Normally, the partition function would simply be this only, what we have derived. Eigenvalue 1 raised to n plus eigenvalue 2 raised to n. That's it. But now, because n is much larger than 1, suppose lambda 1 is greater than lambda 2. Suppose lambda 1 is greater than lambda 2. Then in that case, lambda 1 raised to power n, where n is a very large number, is going to be much, much, much greater than lambda 2 raised to power n. Think about this. 3 raised to 3 is greater than 2, so 3 square 9 is greater than 4, 2 square, right? We're talking about powers now. 3 cube 27 is a huge difference than 2 cube 8. Now if we keep on going to higher powers, then say 3 raised to 10. What is 3 raised to 10? I don't know, I have to check actually. 3 raised to 10. 59,049. And what is 2 raised to 10? 1024. Do you see how much difference does it make? This is already 60,000. This is just 1,000. So here the difference was just 1.5 times. Here the difference became 60 times. This is 1,000, this is 60,000. The difference has multiplied many folds. So now imagine that this power is a very large number. So in that case, this value would be much, much, much larger than this value, and I can simply neglect the second value. I hope this logic is also very clear. Because n is very large, the first term, which is larger than the second term, its power n is going to be much, much larger than the second term power n. The second term power n is practically negligible as compared to the first term power n. So that's why now my partition function will just simply be lambda 1 raised to the power of n. That's why what was my eigenvalue? The larger eigenvalue. So the larger eigenvalue is x plus 1 plus square root of the square root term upon 2. The minus 1 would be lesser, the plus 1 would be higher. So this is simply x plus 1 plus square root of x square minus 2x plus 5 divided by 2. This raised to the power of n is my partition function. X plus 1 minus, no, x plus 1 plus x square minus 2x plus 5 into half raised to n. This is my canonical partition function. I hope this is clear. Let's move on to the next problem. The average energy of the Bohr system is. So the question is, what's the average energy of the above system? How do you get the average energy? Z is equal to simply E raised to minus beta H, right? Trace of this. So minus ln Z 1 by beta minus 1 by beta ln Z. Ln Z is equal to minus beta H. Expectation of minus beta H minus 1 by beta ln Z is equal to expectation of H. Oh, okay. I cannot actually do this. Right, I realize that. So basically, ln Z is minus beta H, expectation of minus beta H. Del of ln Z by del beta actually gives me, and with a negative sign gives me expectation of H, which is the average energy which I seek. So that's why this is my expression. I can't take 1 by beta common outside because the expectation itself actually involves beta. Achha, but nonetheless, I might be able to. Okay. In anyway, but this is the expression for energy. Del ln Z by del beta. Okay. So what is ln Z first? Is just n minus n ln 2. I'm basically taking out the denominator separately. Or let me just write it like this: n log of x plus 1 minus square root of x square minus 2x plus 5 divided by 2 is equal to n ln x plus 1 minus square root of x square minus 2x plus 5 minus n ln 2. That's my ln z. Del ln z by del beta n divided by x plus 1 minus square root of x square minus 2x plus 5. Okay, so now derivative I have to be very careful while taking, because x is equal to e raised to power beta j. So x has beta inside of it. So I've already done this. I'm differentiating this term, the term inside I'm differentiating. 1 minus 1 divided by 2 square root of x square minus 2x plus 5 multiplied by root of 2x minus 2. And this whole will be multiplied by uh, dx by d beta log. So 1 divided by this multiplied by the inside term differentiation, which is 1 minus 1 by 2 square root of this, and there will also be a dx by d beta. J e raised to power beta j. This is n into 2 gets cancelled. This 2 gets cancelled. I have square root of x square minus 2x plus 5 minus x plus 1. The whole divided by square root of x square minus 2x plus 5 multiplied by 1 divided by x plus 1 minus square root of x square is 2x plus 5. I'll have an n also here and e raised to power j e raised to power beta j. Okay, so this is it. Answer terms look different. So as that look, what I'll do is I'll rationalize this term. The term that I've gotten here, I'll rationalize this. So I've already written one n. So let this go. N divided by x plus 1 minus square root of x square minus 2x plus 5. I'm just writing only this part, only this term I'm writing, multiplied by x plus 1 plus square root of square minus 2x plus 5 divided by x plus 1 plus square root of x square minus 2x plus 5. So x plus 1 plus square root of square minus 2x plus 5 divided by x plus 1 the whole square minus x square minus 2x plus 5. This becomes x plus 1 plus square root of square minus 2x plus 5. That remains the same, but the denominator becomes x square minus x square goes away. There is a 2x and there is a 2x. There is a 4x. There is a plus 1 and minus 5 minus 4. 4x minus 4. That's what remains here. So the final term that remains is 1 plus square root of x square minus 2x plus 5 minus x into 1 plus square root of x square minus 2x plus 5 plus x divided by 4x minus 4 into square root of x square minus 2x plus 5. This also might require some evaluation. So let's go ahead and do that. So this is 1 plus square root of x square minus 2x plus 5 the whole square minus x square. So 1 plus x square minus 2x is 5 plus 2 square root of x square minus 2x plus 5 minus x square. Just x square goes away. Okay, so by the way, I'm missing out on this term which also I have to include, and I'm also missing out on this n. This is n, j, and e raised to power beta j is just x. There is an x also here. This term into n j x divided by 4x minus 4 into square root of x square minus 2x plus 5. This, yeah, the solving is actually correct. There's no problem here. 1 plus 2, sorry, 1 plus x square minus 2x is 5 minus x square plus 2 square root of x square is 2x plus 5 njx divided by 4x minus 4 square root of x square minus 2x plus 5. So we've got 2njx. I'll take 2 common outside. What I have inside is 3 minus x plus square root of x square minus 2x plus 5 divided by 4x minus 4 square root of x square minus 2x plus 5. Right. So that's 4x. I have 4x minus 4 in the denominator. So this 2 cancels out 2 from here and I get 2x minus 2. 2x minus 2. And this 2 goes away. So this is exactly what I have. But here this is just del ln z by del beta. Energy is a negative of this is equal to energy. So negative of this will actually have 2 minus 2x. So this I will absorb here and make it 2 minus 2x, which is exactly the answer we have, this one. So that's what happens. That's how you have to solve this one. It's simply algebra. All you have to do is evaluate this expression del ln z by del beta. All you have to do is just evaluate this expression and follow through with mathematics and you will get it. Okay, now in the same above model that we have actually evaluated, uh, we are adding a magnetic field also. What does addition of magnetic field do? When you add a magnetic field, uh, the magnetic field basically the strength of the magnetic field is given by H here. So what happens is uh, it's not exactly magnetic field, it is the interaction of magnetic field with the spin that is given by H. H will have other constants and all also, which directly multiplied with the spin will give you the actual interaction energy between the magnetic field and the spin. So H into spin directly gives you the interaction energy between magnetic field and the spin. So H somehow contains the strength of the magnetic field. So that's somehow telling us to rewrite the Hamiltonian itself. But since we have to rewrite in terms of expectation value of S, so we kind of consider the mean field theory. Just a moment. We will be evaluating this in the mean field manner. Let's do this. Si, which is any spin at the lattice position I, we can write it as average S. This is an average value. This is a mean field value. It is constant for all the spins, irrespective of the position. So this is the mean field value. I will actually start calling this M and then later put it as expectation of S because M is a much easier way to write it. Plus delta Si. The I dependence will be incorporated in the fluctuation part. Okay. So let's go ahead and replace all the SIs and SI plus ones with these kinds of terms. Okay. So H is equal to minus J sum over I equals to 1 to N Si, which is M plus delta Si, and Si plus 1 is M plus delta Si plus 1 plus H sum over I equals 1 to N Si, which is M plus delta Si. Okay, now yes, let's write it. minus j sum over I equals 1 to n m squared plus m delta si plus m delta si plus 1 plus delta si plus 1 plus h sum over I equals 1 to n m plus delta si. Now, um, we are considering this particular model to be near the regime of mean field theory, which means that there is an average field in the lattice and individual lattice points fluctuate above and below that average by a small amount. For example, I can say that the average field in the lattice is say something like 5 microtesla. At an individual lattice point, the fluctuation could be say zero point 0.1 microtesla or 0.05 microtesla, something of that sort, of that order. Small fluctuations above and below the mean field. So basically, if I consider this to be my lattice and I say that expression of S is equal to M is some 5 microtesla. Okay. So individually at every point, the value of the field or the interaction energy, whatever you call it, need not be exactly 5 microtesla, but it can be say 5.01 microtesla here. Here it can be 4.99 microtesla. Here it can be 4.98. Here it can be 5.02. This way. So the fluctuations are small and they are around the average only. The fluctuations are about the average value only, and those fluctuations are small. That is what we call the mean field regime. So here we are assuming that we are already in the mean field regime. So delta Si is anyway small, and the product of delta Si is much smaller. So this definitely we can ignore. The other fluctuations are important or necessary to keep. Otherwise, it will be a uniform magnetic field only. So first order fluctuations we do need to consider. Second order fluctuations are something that we can ignore because the fluctuations are small. I hope this point is clear. So we have, because we substituted it in this manner, S plus delta S, in this manner we substituted. That is why we could actually see the second order fluctuation term properly and neglect it. Now we put it back in the original form. So delta Si, now I'll put it as Si minus delta S, which is Si minus M. I'll start putting it like this. So that's why H is equal to minus J I equals 1 to N M plus Si minus M. M plus delta Si is basically Si minus M into M plus Si plus 1 minus M. Oh, no, 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 sorry. What am I doing? I started substituting the first term. My bad. I have to substitute it here. Minus J sum over I equals 1 to N M square plus M into delta Si, which is Si minus M plus M into delta Si plus 1, which is Si plus 1 minus M plus H I equals 1 to N M plus delta Si. So this is equal to minus J sum over I equal 1 to N M square minus M square minus M square plus M Si plus m Si plus 1 plus h plus delta Si. Here also I have to substitute Si minus m. So this becomes just Si. Okay, so now think about this. We have a periodic boundary condition, right? So sum over m Si, where I runs from 1 to n minus j, and this sum m Si plus 1. This actually, both of these sums are the same, right? If you can understand that, because this goes from ms1 plus ms2 plus ms3 plus ms4, it keeps on going till msn. This one starts at ms2, goes till msn, and then msn plus 1 is ms1 only. So the last term here is ms1, before that it's msn, and so on and so forth. The first one is ms2 plus etc. Here the terms are ms1 plus ms2 plus it goes on till msn. Just that this term here is displaced in this at the end. Otherwise, you can see that both of these terms are the same. So what you can do is you can simply write it as this is equal to minus j m. Now I'll write as expectation of s. Sum over I equals 1 to n expectation s two times expectation of s into si minus m square j sum over I equals 1 to n expectation of s the whole square plus h I equals 1 to n si. Yes, so the first term this is plus 2 minus 2j and this is h. So this seems like the answer. This is the answer what we have derived. If you check this is 2m square into j. 2, sorry, what am I doing here? Wait, sorry, my bad. I'm making mistakes. Uh, this just gave me 1 m square, right? M square j, and there is no s here. This is just sum over I equals 1 to n. which gives me only n, m square into j, which is s square into j, plus. So plus s square into j, this is the first term, plus h si is the second term, and this is with a negative sign, minus 2jm si, this is the third term. So yes, this is what we get as the answer. This is the answer we got. Basically, these are the terms that we get, and we have to fit them correctly with what in the form that they have mentioned. That's it. But we get the correct answer basically. That's the point. And this is how you're supposed to do it. You're supposed to write in terms of some average value and fluctuation so that you can actually eliminate the quadratic fluctuation term. And then once you eliminate the quadratic fluctuation term, you take it back to the average value and SIs, individual SIs, and you arrive at the answer that they expect. I hope this is clear. We basically could manage to remove the second index. We could basically could manage to write the entire thing in terms of only one index, SI. So this is basically what he also mentioned as H effective. It became something like in the form of H effective and all. So yeah, Z equal to sum over e raised to power minus beta si plus 1. No, no, it's not sum over this. It's a product of it. E raised to power beta j si plus 1 say and sum over SIs. Hmm. Right. So now Z is going to be equal to e raised to power trace of e raised to power minus beta h is equal to trace of e raised to power minus beta, and there is a minus sign outside. We'll actually use this answer itself. What is h here? The h that we have derived. That is my h. H is equal to the mean field Hamiltonian, sum equal to I equal to 1 to n m square j with a negative sign outside. No, there is no negative sign. M square j plus h minus 2 to mj into si. right? This is my entire Hamiltonian. Okay, so z is equal to trace of e raised to power minus beta h, trace of minus e raised to power minus beta m square j into e raised to power. Now what we can actually do is trace of e raised to power minus beta sum over I equal to 1 to n m square j. I can separate that out, and that summation will simply just have n multiplied to it, because m square and j all are constants. Beta is also constant. Sum over I equal to 1 to n will just give me beta n m square j multiplied by e raised to power minus beta h minus 2 mj to si is equal to e raised to power minus beta n m square j multiplied by outside trace of e raised to power minus beta h effective into si, where h effective is equal to h minus 2 mj. Basically, this is some effective magnetic field that an individual spin experiences in a system like this. Actual external magnetic field value is given by h, but individual spins experience an external field of h minus 2 mj effectively. So that is what h effective means, and this calculation actually tells us that this is the kind of field each and every spin is feeling. So this is my partition function. Now expectation si. Let's do something of this sort. Log z is equal to minus beta n m square j plus expectation of minus beta h effective si minus del ln z by del beta h effective. Here it becomes 0 plus there's a negative sign beta h effective expectation si. Right? So this is my expression. Expectation si is minus del ln z by del beta h effective. Hmm? Now let's evaluate the trace. Trace e raised to power minus beta h effective si is equal to sum over si. The model that we have been using has only two values of Si, which is Si equal to 0, comma 1, right? So trace actually gives me this 1 plus e raised to power minus beta H effective. And this has to be raised to n. I equal to 1 to n. This is minus 1 by n. This is what we value. Expectation value of Si is minus 1 by n. Del of ln z by del beta H effective. Now trace of I equals to 1 to n minus n. This is 1 plus e raised to power minus beta H effective n. This is the trace evaluation multiplied by e raised to power minus beta n m square j m square j. This is my z. So now ln z is equal to n 1 plus e raised to power minus beta H effective plus some constant c0, which is ln of this. Del ln z by del beta H effective is equal to n divided by 1 plus e raised to power minus beta H effective into minus e raised to power minus beta H effective. And now multiplying it by minus 1 by n gives me Si is equal to e raised to power minus beta H effective 1 plus e raised to power minus beta H effective. This is the equation we get. And what is H effective? H effective is H minus 2mj is equal to e raised to power minus beta H minus 2 Sj divided by 1 plus power minus beta H minus 2 Sj. That's equal to S. So it has nothing in the numerator. So basically what will happen is this will go in the denominator and become expectation S is equal to 1 divided by 1 plus e raised to power beta H minus 2 expectation S j. This is the final transcendental equation I get. H minus 2 Sj beta H minus 2 Sj into beta. This. So this is what we end up getting as the answer. This is my transcendental equation. Why is this called a transcendental equation? Clearly, as you can see, there is an s here, there's an s here. Both sides you have to put some value of s. You have to find a solution which satisfies both the sides. You have to find such value of s which satisfies both the sides of the equation. That's why it's called a transcendental equation. So yes, by solving this question, we have finally finished assignment 6. And for just 1 minute, if there are any doubts, please go ahead and ask me. If not, we can end this session. Are there any doubts? Okay, assuming there are no doubts, thank you so much for attending the session. Let's meet again next week. Bye.